See when I have to accelerate.
Yeah. So I give you.
Be patient.
Okay. Anything I will stand up and you will see that.
No, no, but tell me when there is 10 minutes. 10 minutes.
Yes.
No? 10 minutes.
Okay. Good afternoon. It's a pleasure to be the chairman of the last session of this meeting. And it's my pleasure to introduce you Professor Stefano Boccaletti from Firenze and also China. He will talk about explosive synchronization and Bellerophon states. Thank you.
Thank you, Ricardo. You know that usually when one starts a presentation, thanks the organizer, for the invitation. And since I'm the last one, I think I can interpret everybody of us thanking really the organizer for having put together this wonderful meeting. So I think we should clap. So please have a clap to Hilda, Silvina, Nelima, Ram, and also Gabriel, who is not here. Hilda, sit. Hey, sit. You lost a clap for you. You see? So the idea is discussing with you a little bit about explosive synchronization and these new states which occur in networked phase oscillators. This is a long-standing project that I was interested in along the last years. And you see I have many collaborators to thank. Here there is Javier Buldu and Ricardo Gutierrez who are in the audience, and the Spanish group, and there is another group in Israel, Italy, and then a large Chinese group who is collaborating with me on this project. Synchronization is a very old problem in physics, and it turns back to Christian Huygens, who discovered that when you have two pendula, and you put the two pendula hanging at the same beam, these two pendula start oscillate in sympathy. He called it sympathy, the fact that two pendula oscillated like this, that is actually in antiphase. And he understood very well that this collective phenomenon was due to the tiny forces that the two pendula were able to transmit themselves because they were hanging at the same beam. So he understood that the tiny coupling between these two could produce so to say, a sort of collective behavior which is synchronized or sympathetic, as he said, behavior. Now, turning to nowadays time, one of the models that you probably already saw during this conference, the Kuramoto model, and the idea is to study exactly the same thing, so how oscillators can adjust their phases when you have a very large ensemble of oscillators. And the model that Kuramoto proposed, it's a fantastic model because it's so simple, and it turns out to have a fantastic, huge, incredible scenario rich of dynamics. It's the following. So you have oscillators. Each oscillator is represented by a phase. Therefore, each oscillator you can imagine to have like a point here in the unit circle. The derivative in time of the phase is nothing but a frequency, so simple. And in absence, therefore, of any connection, you have a collection of points that are rotating or counter-rotating depending on the sign of these frequencies. Then the model considers a very large ensemble of such oscillators, and it assumes that the frequencies of these oscillators are slightly different, and they're taken usually from a frequency distribution G omega. So G omega here, look, is one of the first ingredient of the recipe that we will use them after. Okay? So G omega is the distribution of frequencies that are given to our oscillator when these oscillators are uncoupled. Then you take a large ensemble and then you couple. And the idea of Kuramoto is coupling them is just having a scalar value d, which is called the coupling strength, times the sum of the sinus of the phase difference. So these oscillators are all-to-all coupled, and they feel the sinus of the phase difference among them. Now, what I want to show is a movie to show you what happens when I take many of such oscillators and I increase d, the coupling strength, okay? For visualization, I put this oscillator on the unit circle in different positions and slightly distributed around unity. And then what is happening is the following. The green line is the unit circle. So what you will see is that when you increase d, you start from a completely incoherent set of oscillators, that is each one with its own phases, and then they start grouping together and acquiring the same phase and the same frequency, of course, because they are moving together synchronization is exactly this. A big bunch of oscillators which together acquires the same phase and the same frequency. And what I'm going to discuss today is the transition to this phenomenon. So you have a system, therefore, that has two phases. One phase is this, when the oscillators are all separated. The other phase is the coherent phase, when all oscillators have the same phase. And what I want to describe is the transition between these two phases. Okay? In order to monitor this transition, typically one relies on this order parameter, which is nothing but the sum of the vectors, of the unit vectors that corresponds to each oscillator. So when you are in the incoherent phase, this sum is 0 because this vector and this vector, when you sum up, they basically make 0, so they erase each other. Whereas in the fully coherent phase, you have a unique phase, so a unique direction of these vectors. You sum them coherently, and you have here something which is of the order of n. So when you divide by n, you get something of the order of 1. The transition is therefore the passage of this parameter, the order parameter, from 0, the incoherent phase, to 1. So what I tell you again, I have this incoherent phase, I have this partially coherent phase, and I have synchronization. And I want to anticipate you immediately that the key point is what is happening in between. So this state of the system is very clear. Each oscillator is almost free. We call it like a bath, a thermal bath of free-running oscillators. This order is also clear. I mean, everything is locked, so you have unique phase, unique frequency. So what is crucial is understanding this. Now, I can anticipate what is happening. Let me anticipate later. So now I just skip a few things. I add only that we studied this on network. So with respect to the Kuramoto original model, what we have to do is to plug here the adjacency matrix of the network. So basically, the only thing that changes is that this matrix tells you which oscillator is connected with which. And then, you know, when you have a system having two phases, in general, in physics, you have two kinds of transitions. The so-called second-order-like transition, which is a continuous transition. So here, here there is a mistake. This is not the order parameter, it's the control parameter. And this is the order parameter. So you have a control parameter and you have an order parameter. When you increase the control parameter, it continuously passes from one phase to the other. Typically, this is a phenomenon typical of reversibility in the sense that I can prepare my system here, increase the control parameter, and I will make this curve. But I can also prepare my system here in the other phase, decrease the control parameter, and I will have exactly the same curve. So second order like transition are usually characterizing reversible processes. And then you have also instead the first order like transition, which are characterizing non-reversible processes. First of all, they are not continuous, they're very abrupt. So the system stays here and then jump suddenly to another point, to the other phase. And it's not reversible because in the forward transition, I jump in this position, whereas in the backward transition, I jump in this other position, i.e., I create hysteresis. So I want to discuss now what happens when we prepare some thing in the Kuramoto model for having such kind of transition instead of such other kind of transition, which I call explosive synchronization because you have this abrupt change. Oh, let me go back and I tell you that everything, really everything, depends on what is happening here. Normally, the transition of Kuramoto is second order like, is this. What is happening is that this transition is made in the following way. Here I have a thermal bath of independent oscillators. Then suddenly, for some value of the coupling strength, 2 or 3 oscillators, which have, by chance, their original frequency close by, they form a seed of synchronization. So you have a very small cluster of synchronization which coexist with this thermal bath of free-running oscillators. You can create 1, 2, 3, many of such. Exactly here. Then this cluster can do 2 things when you increase the coupling strength. One is to grow in size. They attract to themselves some other free-running oscillator. I have many free-running oscillators. So there are 2, I take another, and I grow. The other thing that it can do is to merge. I have now 2 clusters. Imagine to have 2 clusters, okay, with 2 different frequencies, and suddenly, bloom, they merge together and form a unique, larger cluster at a unique frequency. So this that you can see here is a process of growing, merging, growing, merging, growing, merging, up to the point in which the system has a unique, giant cluster, the entire system, with a unique phase and frequency. So you arrive to this phase. Okay? So the process, the continuous process is a sequential, so to say, is a sequence of growing and merging of this cluster. The key, if I want to have a first-order transition, is I have to freeze my system. So I have to put some processes that impede to my cluster either to grow or to merge. So I then freeze my system here. I force my system not to form cluster, not to grow cluster, not to merge cluster, up to a point which my coupling strength is too large, and so I have to jump up to the other phase. Clear? So we are going now to play with the ingredients of the cake, with the ingredient of Kuramoto, in order to impose this kind of frustration mechanisms. And the ingredient of Kuramoto, okay, it's here. So I have 2 ingredients. One ingredient is, already said, G omega, how I distribute the frequency to my oscillators, and the other ingredients, how I couple the oscillators. So the structure and the distribution of frequencies. And let's go and let's start the story. So the story starts with this very nice paper by Diego Passot, who made the following. Observe that if I now distribute the frequencies, he took the original Kuramoto, so all-to-all connected, and he distributed the frequency in a very particular way. in an equispaced way. That is, you put the frequency omega here, omega plus delta, omega plus 2 delta, plus 3 delta, plus 4 delta, plus 5 delta, okay? And you notice that if you do like this, you obtain an abrupt transition, discontinuous transition. Now, the problem is that, one, this particular realization is a measure zero realization of a homogeneous frequency distribution. So it's very, very particular realization. And indeed, what he noticed that if you move away from this realization, you put a little bit of noise, just a little bit of noise, you return to the continuous case. So it seems that you can have in the Kuramoto model discontinuous transitions, but for very, very particular and specific realizations. Then there was another paper by the Spanish group of Jesus, Alex, and Yamir, and they claimed that the necessary condition for having such discontinuity is to have, at the same time, heterogeneous networks, so scale-free networks, and have a particular correlation between the frequencies of the oscillators and the degree. So if they impose, for example, omega to be proportional to the degree of the node, so that the hubs are the faster oscillator and the other are the slowest oscillator, they obtain indeed such explosiveness. And you see, if they correlate, but do with some random network, so not with heterogeneous network, again, they get continuous. And if they do with scale-free, but not correlate, they continuous. Now, we will see very soon that this is, in fact, not a necessary condition, it's a sufficient condition. But indeed, this is sufficient to produce things. And again, you see, this is a very particular case. Why? Because it means that once you have a frequency, once you have a degree distribution, the frequency distribution must be the same. Moreover, it's even more measure zero with respect to the other one, because in the other one, being all-to-all connected, you can make all permutation of frequencies, and here you cannot make a single permutation, because the frequency of the oscillator should be exactly the degree. So you cannot permutate two frequencies. So again, this is a very particular cases. And so we started our analysis, say, let's first to demonstrate that these abrupt transitions are not so particular, are much more general, okay? And to do this, okay, so first of all, I told you it's a sufficient condition, so together with Javier, we built an experiment with electronic circuits, and we showed that indeed you can see this experimentally. And the second point was, let's generalize this, the case in which we want to have. And so the first step was the following. So I have two ingredients, the G omega and the network. And the first point is, let's demonstrate that for each G omega you give me, I can always find at least one network that makes this G omega to explode. Okay? So now G omega you give me, and therefore if you give me G omega, it means that the frequencies of my oscillators are fixed.
Whatever the G omega is?
Whatever the G omega is. So you give me G omega, and I give you the network. This is point number one. So you give me G omega, so you give me the frequencies, you choose the frequencies, and now what I do is I pick a random pair, and then I check the difference in frequencies between the two oscillators. And only if the difference in frequencies of the two oscillators is larger than a given threshold, gamma, I put a link. So what I'm doing, I'm constructing a homogeneous network like an Erdős range, but conditioned to the fact that no links are existing between two close-by oscillators in frequency. So I'm forbidding the formation of the small cluster, because the links only link oscillators which are far away in frequency. You understand? I'm putting a frustration mechanism on the formation, so it's called like a gap in frequency to the formation of these links. I continue putting these links up to the point in which I get the desired network, so the desired number of links, and I use the resulting Aij, and here is the result. When gamma is equal to 0, so I have no threshold, I grow an Erdo-Range network, because I always put a link, I have, of course, continuous transition, like the usual case. When I increase gamma, I arrive to a point, gamma 04, in which I have DAP and DAP, hysteresis and abrupt transition. And this is valid for whatever G omega you give me, because we proved this for homogeneous, for Gaussian, Lorentzian, symmetric, asymmetric. But much more interesting of this is that what happens now? Look at this. If I am this oscillator, I cannot form connection with oscillators which are close by in frequency. So I can only form connection with this and with this. So my expected degree will be the integral of G omega on this region and this region. So I can analytically calculate the expected degree of the node as a function of this frequency. And when I do so, okay, moving the window in frequency, when I do so, I obtain the following, that for whatever frequency distribution, we get indeed explosiveness, and in connection to this explosiveness, we get a V-shaped correlation between the degree and the frequency. So first of all, it's a V-shaped, it's not linear like it was said before. And it's emergent, it's not superimposed. That is, it's due to the construction of the network, not we impose a priori such condition. And this is valid for whatever G omega, and you can even relax the condition. Instead of having a threshold on the difference of the frequency, you can have a threshold on the difference of the frequency minus the average frequency of a neighborhood, whatever you want. So this is step one. You give me G omega, I give you the network. Now step two. Now you choose everything. You choose G omega and also the network. And I want to demonstrate that if you give me G omega and you give me a network, I can always put a series of weights in the link so that you can explode. Okay?
Non ho trovato Waze and Lyrics tra I tuoi brani.
Siri, sorry. Siri, this artificial intelligence. Yes. Okay, so what you do again, so now you give me the omega here, and you give me also the network. So I cannot touch, cannot put more link, I cannot cut. What I can do is I can put weight, and the idea is very similar. I put a weight on each link, which is proportional to the frequency difference between the two nodes to a power alpha. So that the more distance they are in frequency, the higher is the weight of the link. The closer are in frequency, the lower is the weight of the link. And look what happens. When alpha is equal to 0, again, you are not waiting, because everything is 1. So you have a very nice, indeed, second order like transition. When alpha is equal to 1, you have something very nice, because you have a sort of universal first order like transition, Universal in the sense that no matter which is the frequency distribution that you use, you can use uniform, Gaussian, bimodal, Rayleigh, semi-Gaussian, you always find the same forward transition and the same backward transition. So I have only 10 minutes. I have to accelerate. I have many, many other things to tell you. Again, you have formation of correlation, and you have also the possibility of modulating the length of your hysteresis with the betweenness of the network. Okay? So there is a lot of things you can do about this transition. You forget about this. Now, next step is the Bellerophon states. The Bellerophon states is the following. Now I will tell you about the states, and then I will tell you why I call them Bellerophon states. Because they are the opposite of the chimera state. So Bellerophon was the Greek hero who killed chimera, and so we have to. So I think, I hope I have convinced you that in the Kuramoto model, you can prepare things so that you can be either second order like or first order like. So if you can do so, what you can do, you can prepare the system in a way that depending on a parameter, you can be first order or second order. So what we do is take here the Kuramoto, you put here Ki, so each node has a specific coupling strength to the mean field. This Ki is nothing but K times the frequency of the node. And then we use a bimodal Lorentzian distribution. And immediately you realize that depending on this parameter, omega 0 divided by delta, where omega 0 is the location of the two peaks, and delta is the width of the two peaks, you can be first order or second order. So now the point is, here I have clusters, here I don't have clusters. If now I put myself exactly on the three critical point, where there is a passage between second order and first order, should I see cluster or shouldn't I? Because on the right I see, on the left I don't. Okay? And so the idea is, let's then put ourselves exactly here when there is a transformation between this, you see, residual first order to a pure continuous, and see what happens. Fortunately, the system is still integrable. So what you can do, you can solve for the backward and forward transition separately, and you have exactly analytically the value of this three critical point, which is square root of 3. So you put yourself exactly there, and now see what happens. I'm reporting here three things. Here is instantaneous phases of all oscillators. Here is instantaneous frequencies of all oscillators. And here is long time average of the instantaneous frequencies of the oscillators. Small coupling, nothing is synchronized, so phases are completely unsynchronized, their frequencies are completely unsynchronized, and nothing happens also in the theta dot average. Large coupling, everything is synchronized, so they have a unique phase, unique frequency, unique long time average frequencies. What happens in between? In between, you have formation, you see, of these clusters. These clusters are visible in the average frequencies. Members of each clusters are not locked in phase, not locked in frequencies. They are mode locked. In the sense that if you look this, for example, this cluster, this corresponds to a cusped pattern of instantaneous frequencies. And the instantaneous frequencies of each oscillators are time-dependent and periodic signals, okay? So here you see, for example, other cases. And in practical, what you have is the emergence of a quantized cluster, because this plateau are odd multiple of the fundamental frequency, in which the element of each cluster are not phase nor instantaneously frequency locked, but the instantaneous frequency have a long time average which is constant. So they behave periodically in time, and their average values are the same. In order to appreciate what is happening, I show you a movie, okay? In this movie, what I did is I collected here in this unit circle all the elements of cluster 1. Here, all the elements of cluster 3. Here, all the elements of cluster 5. Here, all the elements of cluster 7. 1, 3, 5, 7, because they are odd multiple. You will see that these elements are not phase locked, but they go from one side to the other side of the unit circle, and in the period in which these elements do it once, these elements do it 3 times. These elements do it 5 times. These elements do it 7 times. Okay? Which is responsible for the scaling of the frequencies. So look, the clusters. No. Don't look this, look this. You see, they collect here, then they disperse. Just a moment, and they recollect there. They stay a while, they disperse and recollect here. And in the same period, this will do this 3 times. This means that corresponding value for the why it doesn't work? You see? Look how beautiful are this pattern of instantaneous frequencies and phases in each one of the cluster. 5 minutes, sufficient. Because of this property, if I now take each one of the cluster and calculate in each clan of the cluster the order parameter, instead of having a constant, I have a time-dependent evolution. So I take elements of cluster 1, and you know the order parameter is a complex number, so I represent real and imaginary parts, and then here I have a period 1 phase limit cycle. If I take elements of cluster 3, I have a period 3 limit cycle. If I have elements of cluster 5, therefore a period 5 limit cycle. And you see this is the evolution of R for the phases for different elements. So you see very well that, for example, these 2 oscillators which belong to the first cluster, they have a period 1. This one, they have period 1, 2, something like period, double period, but with 3 times the way, and so on. Then, again, so you can object. This is very nice. It's a completely different collective motion that you can find, because it does not correspond to the setting of a phase. The instantaneous phase is completely unlocked here, and the instantaneous frequency is completely unlocked. You have a higher order of, so to say, coherence there. But you can question that this is not so general, again, because it depends very much on the fact that since the beginning, each oscillator is coupled differently with the mean field. And it's coupled depending on the frequency. So the faster oscillator are more coupled to the mean field, the slower oscillator are less coupled with the mean field. So we decided to see, is that more general? And in order to take something more general, we imagine that in fact, this K value could have only 2 values, a positive and a negative. This is a very nice case which was studied by Steve Strogatz in the past of an equal, the 2 population of contrarians and conformists. So there is a group of oscillators which are positively coupled to the mean field, so they are conformist because they follow the mean field, and there is another group of oscillators which are contrarians because they oppose to the mean field. Then Steve has shown that when the system is only composed by contrarians, then there is no synchronization, and the only possible state is the incoherent state. But then when you take a portion of contrarians and you flip into conformist, then you can have appearance of synchronization. And more precisely, when a proportion of conformists exceeds a certain threshold, you have a transition to the coherent state. Now, in order to take and to flip these oscillators, you can do it in various ways. For example, you can take a fraction of contrarians and flip them randomly to conformist, or you can follow the frequency, the frequency order, so you from the maximal to the minimal, or from the minimal to the maximal. So you have a matrix of possibilities, the 3 cases, and then 3 possible values of the coupling strength. And you see that for all cases, the passage between the incoherent coherent state is mediated by these states, which are the Bellerophon states, which have exactly the same characteristic as before. So to have plateau in this average frequency, but to be completely unlocked in instantaneous frequency and instantaneous phase. Then you can have mixed state. I don't want to enter into more details. The person who are interested can have a look to this literature. Synchronization, networks, explosive synchronization. It's a long list of papers we published, you see, from 2012 to 2016, and the recent papers on Bellerophon states. Only 1 minute to tell two things. The first is this. Please submit your best paper to Chaos Oscillators and Fractals. It's a very nice, very, very nice journal. And this year we are very proud because we converted ourselves in the most prestigious venues for statistical and nonlinear physics. We got, I don't believe too much in impact factor, but we got 3.064, which make us the third venue in mathematical physics and the fifth venue in interdisciplinary physics and the top venue in the world for statistical and nonlinear physics. So please make use of this journal. I will tell you something more about the journal later on because we have a prize of the journal, so I don't want to spend too much time here. And the other thing I want to tell you is this. It's a conference announcement with some other crazy guy, especially Bill Ditto. We decided to organize, to make a trial, to organize in Madrid next year, 15, 18 of June, a conference called Manifesting Intelligence, which is the idea of exploring a little bit the crossroads of artificial intelligence and nonlinear dynamics. So we invite, please, if you have ideas and so on and so forth, contact us. Here you have the three mail. And the main idea here is really to create a sort of bridge because artificial intelligence is the future. And we really believe that we as nonlinear dynamicists has a lot to tell to these people because intelligence is an emergent thing. Cannot just seen as a more fast computation. We have the best computer here, performing 1 trillion of operations per second, and is powered by a dish of pasta per day. In my case, a little bit more. And whereas the largest and fastest computer in the world, you need half a nuclear power grid to power it, and it does not get to 1 over 10,000 the capacity of our brain. So we should better understand our brain and make some new hardware and software that works a little bit better. And this is the idea of the conference. Thank you a lot.
Stefano, thank you for the very nice talk. We have time for a few questions. Murilo?
What is the coupling parameter? What is the coupling range for the Bellerophon phenomena?
Sorry. I took out the, just a moment. It's the entire coupling between the two synchronization regions. So, goes, yes. So look at here. I go to the first example, which is a simple one. It's from here to here. So A, B, C, D are the value of the coupling for which you see these things. Okay? I don't want to comment because I have no time. I leave you this, which is the comparison between Chimera state and Bellerophon state, just for you to understand it's exactly the opposite. It's exactly the specular state with respect to Chimera. Chimera is coexistence of order and disorder, locally coupled, identical oscillator, Caspet pattern of time average frequencies, and question mark if they are asymptotic state. These are asymptotic state but non-stationary, because I told you that they are non-stationary, these are stationary. This is a coexistence of cluster with quantizing, globally coupled, non-identical, you see, the opposite of this. Then oscillators in each cluster are not locked in phase, not instantaneous frequency, but what's most important is the Caspet pattern, the same as Chimera, appear here in the instantaneous frequency, not in the time average frequency. You know, it's really the... Okay, sorry.
Any more questions?
Yeah, just a comment. I mean, it calls my attention that you have done these things, and it seems to be that the important discovery is that what you have to compare in some of these systems is not the instantaneous frequency, but their average or wrong-time behavior, as you want to call them. I mean, I'm sorry, this is going to look like advertising, but there were lots of papers by people like Strogatz, Hugang, and also myself with several collaborators in which particular cases had been worked out of this and shown that precisely those systems behave like that on the average frequencies while having all the other properties that you were saying. That, I mean, it's not that it diminishes anything. What I'm saying is that it's just a particular case to which to compare, I mean, the results.
I mean, so, I agree in the sense that
wait a second. The last one we published on that was an analytical calculation of the synchronization point. Is it chaos, oscillators, and fractals?
Good. Very good.
Okay.
No, I accept, and indeed, I want to tell you that both Chimera and Bellerophon states are states which are, I mean, very difficult to find. Also, Chimera state is very difficult to find. You have to find some specific initial condition. So, but they are interesting, at least, for example, one thing that we could not solve yet is, this is a completely classical system. Completely classical. And you have the emergence of quantization. How this omega 1, I mean, this basic frequency such that the first cluster is omega 1, the second is 3 times omega 1, 5 times, how this is related, this is my H bar, okay? So how this is related to the main parameter of the Coulomb model. This we did not found because we don't have an analytic solution in that these are not stationary states. So you don't have a stationary states on which to write reduction like Otto-Antonsen and whatever.
Okay, I'm for just one more question.
One simple question. Is there any real system showing these Bellerophon states?
It's a state that is compatible with Kuromoto. Is there any real system which can be described by Kuromoto? Model, I mean. If it is described by Kuromoto, you can find some in this system, some parameter or region or area where you can expect to have this. So it's Kuromoto system. It's the Kuromoto model in which you play with some ingredient. I tell you, I was telling today Ram that Kuromoto was very lucky because he wrote a very simple model with only just the linear term, and it has tremendous things inside. So this is one thing that you can find in a particular proximity of a critical point. It's not so general. Generally, if you have Kuromoto, you have second order transition, but.
Okay, so let's thank our speaker again. And this session is closed. I will pass the word to Hilda for the closing of the meeting, or Ram.
Well, I thank you all for coming, but before even finishing the thank you for coming, I am going to call again.
Primero te pones esto.
Gracias.
And my camisa is very pretty.
No, but I don't need, I need this. Yes, you're right. I have to leave this here. Well, the thing is, before closing and everybody going to have the beer for celebration, I have to call again Stefano, who will give us some good news.
good news. I don't know if good or
Take
bad.
this.
No.
Well,
It's
for
not,
someone-
but I look at here.
For
I follow you.
For someone will be good news.
So you are the one attracting the camera. I wanted to spend a few words about chaos oscillators and fractal and chaos oscillators and fractal X. I told you already that the journal now grew a lot, and we are very happy. We want to grow more. I want to have this journal, in particular, also as a venue for people from Latin America. So please send us your best papers. And recently this year we at Severe decided to open the open access mirror journal of chaos oscillators and fractals, which is called Chaos Oscillators and Fractal X. This is a particular experience because you know that usually open access journals have critics that they tend to accept more papers because they make money on accepting papers. Of course, they have to have fees. And we decided to do this idea of the mirror journal because submissions is blind in the sense that I am the editor-in-chief, I received the submission, and I don't know if the author submitted this paper for chaos oscillators and fractals, so the regular venue, or for the open access version. So I have to process the paper exactly in the same way, to send exactly to the referee and process exactly in the same way. So there is completely the same editorial process. And then only at the end, if the paper is accepted, the author discloses where they want to publish. So in this case, we will make an exception because we have made a prize, so I know that what they will submit will be for the open access. But we decided with ILTA to offer a prize of the two journals to this conference, which was given to the best poster. And it consists in a little amount of money, very little, plus a wild card that is the recipient of this has 1 year of time to submit a paper to our journal. And if the paper will be accepted, he will not pay any fee. So he will have the possibility to publish on open access journal, without any fee. Now, Javier helped me a lot because he decided together with Hilda and Ginestra and who else? And Cristina Masoyer. So they told me that it was extremely difficult because the posters were fantastic, so they were completely undecided, very long night of discussions, a lot of caipirinhas. So they also asked to several guys, how many caipirinhas you give me if I give you the prize? But eventually at the end, the prize was given, and the recipient of the prize is José Trobia, or José Trobia. From Universidade Estatal de Ponta Grossa. Here is the certificate. Thank you a lot. Thank you. Obrigado. Thank you also to the jury, and please, Hilda.
Congratulations.
Thank you. Thank you. Don't lose the envelope because there is the money inside. Yeah, it's not that much, but if you lose, it's worst. And and you have 1 year of time. Please submit really to our journal the best, and to everybody, use our journal. It's an open journal. We will be very glad to receive more and more high-quality papers because this is our mission to serve the community the best we can. Thank you.
Thank you very much. Would you like to say something?
Thank you, Professor. Thank you, everyone. Thank you. Choose in the work. Ok. Português? Pode ser?
Fala português.
Fica mais fácil. Agradeço aos professores, então, pela escolha do trabalho do grupo de Ponta Grossa, o qual o professor Batista é o meu orientador hoje, ok? E espero, em próximas oportunidades, né, ao participar desse evento, já poder apresentar, né, de uma forma diferente do pôster. Agradeço a todos. Né? Thank you very much.
Muito obrigada. Well, I guess that we are about to close the